Hi, everyone. Welcome to the Tartan SLAM seminar series. Today, we are excited to have Krishna Murthy as the speaker, giving a talk on differentiable programming for spatial AI, representations, reasoning, and planning. So his research aims to interweave classical approaches in computer vision and robotics with modern machine learning, with the goal of building flexible, interpretable, and actionable models of the world for robots. He's a recipient of the Best Paper Award at RPL 2020 and RSS Pioneer 2020, and is best known for his Grad Slam library. And with that, I hand it over to you, Krishna.
Thanks for the very gracious introduction, Paloma, and it's good to be here. Thanks for inviting me in the first place. And I've been catching a few talks on and off, and there was some really interesting content presented and discussions generated. So I'm also looking forward to some of the other talks in the series. But yeah, today I'm going to be talking about a topic that I've been fascinated about for the last 3 and a bit, like maybe 4 years. And that's more about differentiable programming and how it can impact various components of the robotic stack. And just before I begin, a bit about myself. I'm currently located in Montreal. I'm a final year PhD student at Mila, and I work with the Robotics and Embodied AI Lab, which is directed by Liam Paul. And we're currently a small group, but there's the larger ML group at Mila that works not just on robot learning, but in various aspects of AI. So this is, I think, from 2.5 years ago, and hopefully we'll get to see a gathering like this sometime soon when conditions are safe and everything opens up. But that's one reason I like putting this slide up in the beginning of every talk. So yeah, like since this is a SLAM seminar series, I don't need to introduce SLAM, and I will not go about talking as to what are various kinds of SLAM systems and what they can and cannot do, but rather I want to just describe my journey into SLAM. So when I started working in SLAM, sometime during my master's, I ended up like just reading some of the early papers on SLAM and some of the more recent papers, and everyone that I talked to spoke of SLAM as though, SLAM is the central problem in robotics. Once you solve SLAM, it just opens up possibilities to lots of new, exciting things. But over the years, especially over the last 2 years or so, I've begun taking this view that SLAM is more of a means to an end. So mapping in general is not a requirement for most robotics tasks of interest. And if you look at robots doing various tasks, or here, the end goal for robots is, for example, here to put all the trash into the trash can, or like rearrange this table, or some surveillance, or drive from A to B without crashing. None of these tasks explicitly require us to build a map. But over the years, we've come to notice that if you have an explicit map, then it opens up, it makes reasoning much easier. You can plan over the map and then do control and so on. But the important thing to realize is SLAM is always a means to an end. And SLAM, the goal of SLAM is to provide you with a good representation of the environment. And everything that comes after operates on the representation to solve a task of interest. And so because of this, a lot of SLAM research has either directly or indirectly focused on the question of map representation. So if you looked at several years ago, SLAM research almost entirely comprised occupancy grid style maps. And with the advent of other kinds of sensors and other kinds of tasks that robots are deployed in, you get all of these other kinds of maps that I show on the top row. So you see LiDAR or RGBD maps. And the top row here was somewhat curated to showcase metric maps. So all of these maps are metric in the sense that they obey metric properties. But then for reasoning, and especially for high-level planning, you often need to reason about things that are not in close proximity of each other. For example, you want to get from A to B, you need to reason about your goal and how you're going to get there. Or if you want to rearrange the environment, you need to reason about how you're going to pick objects up and where you're going to place them and so on. So there's topological representations, or a mixture of them, like topometric representations that I show below. These vary from something like a roadmap comprising traversable nodes to like object-centric maps to all of these purely relational symbolic abstractions that high-level planners use to accomplish or compute a task plan. So there's been so much research into map representation that there's so many possibilities, like so many options for representing maps, but there's fundamentally been a divide in the way that people have approached building maps. So I'm going to talk about first classical robotics, and by classical, I do not intend to mean it's outdated or old, rather talking about robotics before deep learning came into the picture. So a robot stack was very nicely chunked up into these three main modules. There are a few others, but I like to visualize this as, you have a robot equipped with sensors and actuators. The sensors provide you a lot of data, raw measurements from the environment, which are fed to a perception module. And the perception module provides or produces an environment model. And this model of the environment, along with a state estimate, is used for high-level planning, like what do you want to do given that you're in this state? For a self-driving car, this might mean, you're currently here, this is how traffic's moving around you. What do you now do to like get to your destination, minimizing the amount of time you want to travel? And then there's the control module, which takes into account the planner and other constraints imposed by the robot model and the environment, and comes up with control actions that the robot then executes. And this cycle keeps repeating over and over again. But in modern, like model-free learning-based methods, we've begun to see a new trend emerging. So you have a bunch of sensors that directly produce data that are fed into usually large neural net, either a single neural net or a bunch of neural nets, and they produce actions that the robot then executes. And then you have some kind of monitoring system that assigns a reward, or you have some way to supervise the system. And then you backprop all the way and learn representations that are task specific. And most of my research focuses on identifying a middle ground between these two extremes. One where there's very little room for learning, where there's too much structure, and one where there's a lot of lack of structure. So I try to tread this divide while leaning more towards the paradigm where you still try and impose structure. And here's like one slide trying to showcase what's good and what's bad about both of these paradigms. So classical techniques, they're interpretable. That's really useful if you want a human to kind of debug or teach a robot at some point. And you have performance guarantees for certain subcomponents of the system, and the modularity means you can swap things in and out and so on. But on the other hand, you need to handcraft these systems so that they work well in conjunction. And there's also a view that the more number of modules you have, the more points of failure you have. And you need oversight in trying to tune the inputs and outputs of each module and some kind of hyperparameter so that everything works well in conjunction. But that's not the case with learn methods, but they have like the other set of drawbacks. You want to be able to interpret them, and you might want to have performance bounds, at least on components of the system. So what's primarily the reason that such a system does not exist yet? And like the idea that I'm gonna keep throwing repeatedly during this talk is maps need to fundamentally be task driven. So the the upper half of techniques here, like the classical robotics techniques, they build general purpose maps, things like occupancy grids, point clouds, and so on, which essentially are applicable to a wide variety of tasks. But as I'll continue to discuss later, these representations do not tend to scale for other downstream tasks, especially planning, when the size of the representation tends to grow too much. And the idea that I'm going to revisit is you need maps that are somehow tunable with respect to a task specification. And the reason we're not able to do this in at least the classical robotics stack is that you currently have these 3 different modules which operate, which have different input-output signatures and so on, but you can't train them end-to-end with respect to a task, a performance signal, because you need to be able to take the task performance signal and like assign it, do some form of credit assignment to which module actually caused task performance to deteriorate. And the premise is classical models are usually non-differentiable. And if you can somehow make these differentiable, you have a pipeline for learning these representations given a task performance signal at hand. So one idea that I'm going to be revisiting is redesign some of these classical modules so that they become differentiable. And here's just a quick detour towards differentiable programming before I begin to talk about one of our first approaches. I presume a lot of you would be familiar with differentiable programming, especially if you worked with deep learning or any of these libraries. So the core idea in differentiable programming is atomic operations are always differentiable, or you can pass gradients through them by some approximation. And then you can compose all of these atomic operations to form these computation graphs, which you can compute derivatives through by applying the chain rule recursively. And differentiable programming has seen a lot of success in allied areas of robotics. So there's differentiable optimization, differentiable physics, and differentiable rendering is being used for inferring, for basically doing inverse graphics, inferring material properties and so on from images. So the idea is, can the robotics community build off of some of these success stories and like build structured models that make learning easier and interpretable? So for the remainder of this talk, I'm going to be focusing on 2 recent approaches. First, I'll talk about Grad Slam, which is a differentiable 3D mapping framework. And then I'm going to talk about some of our recent work on task planning over 3D scene graphs. So Grad Slam was something we submitted to ICRA now a year ago. And this was, again, joint work with Ganesh, who was a student at CMU at that time. And yeah, of course, Liam is my advisor. So in Grad Slam, the core idea was, can we redesign a SLAM system so that it is end-to-end differentiable? So the core idea is, if you think about SLAM as a function, so it takes in a stream of sensor data, we denote it by S here, and produces a trajectory and a map, so some form of state estimate. And the mapping that we're interested to learn is, let's say if you were to perturb your sensor data by some infinitesimal delta S, how is your output of the SLAM function going to change? So, and mathematically, the change in the output as you perturb the input is going to be the gradient of this function. And the idea in Grad Slam is trying to differentiate through the full SLAM pipeline so that we actually get differentiability with respect to all of the parameters in the earlier parts of the SLAM pipeline. So here's one case study I'll be talking about. And this is the very popular Kinect Fusion SLAM system. And Kinect Fusion is a dense SLAM system operating on RGBD images. So takes RGBD images as input, and you perform some form of surface measurement, which gives you vertex normals and a local reconstruction. And the local reconstruction is noisy because you only have partial sensor observations now. And you want to align these local observations or local map with a global map, which is initially empty, but as time progresses, it gets all of the signal and discards all of the noise from each local map. And there's various components in this pipeline, including raycasting, ICP, and fusion, which are inherently non-differentiable. And the idea of Grad Slam is, can we take these operations within a SLAM system and re-engineer them so that they become differentiable? So there's several moving components in Grad Slam, but for the purpose of this talk, I'll go into detail into one of the components which I personally like the most, which is a differentiable trust region nonlinear least squares. So the idea of nonlinear least squares optimization pervades through most components of the SLAM pipeline. If you want to perform scan matching or get visual odometry, or even perform post-graph optimization, the best approach that's currently used is some form of nonlinear least squares. And the idea is you have this very simple one-dimensional loss surface here for visualization purposes, and you have a cost function, which is a sum of square residuals. And the idea in nonlinear least squares is you just keep following the gradient until you reach local minima. And this local minima might not necessarily be globally optimal. So your initialization plays a crucial role in nonlinear least squares. Since the loss surface is nonlinear, one very common way to solve this is using the Gauss-Newton method, which takes an initial guess and linearizes the cost function around that point. So you get a linear approximation of the cost surface, and then you take one gradient step along that direction, and you relinearize, you take another gradient step, and you keep doing that. But the drawback here is you're not guaranteed to converge. So for example, let's say you're here and then you take a gradient step, you might find yourself on almost the opposite side of the lost surface and you would diverge. And there's also issues relating to the Jacobian being near singular, and that causes optimization instability. So there one way to address this is by using Levenberg-Marquardt, which is a trust region optimization method. And the idea of a trust region optimization method is to tread carefully on a loss landscape. So just imagine as though the terrain is very, very shaky and you want to take steps. So you'd be very, very careful in taking steps. The idea with Levenberg-Marquardt is you would take a step only if it seems promising. So a trust region optimizer would give you a loss, like an estimate that is no worse than what you had to begin with. And the way LM would work is by introducing the slight perturbation over each diagonal element of J transpose J. Oops, sorry. I was just distracted by a notification, but yeah. So the idea here is you kind of have an initial guess and you see where the initial guess takes you. And if the initial guess is taking you away from the current loss surface, so if it takes you to an acceptable value, you take the step, but if it does not take you to an acceptable value, you decrease. So in this case, we see that it's taking us to a point that has a higher loss. So you would not take the step, but rather you would shrink the step size and you would keep shrinking until you got to a reasonable step, like a step that would actually reduce the loss, and then you'd end up taking that step. But the key issue here is this kind of a process that does a look ahead operation and only takes a step if it's safe, that's non-differentiable. So the idea here is it's very similar to what you have in classification problems in usual like ML contexts. When you want to do binary classification, you want to have either 0 or 1, but nothing in between. So you use a smoothing function pretty much like a sigmoid that has most of its density concentrated either at 0 or at 1, but very little density in between. So that's what we do here. So we design a generalized logistic function. It's different from a sigmoid in that it does not range between 0 and 1. Rather, it ranges between the minimum and maximum possible values of the damping coefficient. And it's encouraged to be at one of those values. And this reparametrization makes the Levenberg-Marquardt step fully differentiable. And you can just keep unrolling this over a sequence of steps, and you get a fully differentiable computation graph. So the idea here is where LM would typically be non-differentiable, you'd get smoother gradients around like a wider region. And we have a few other differentiable components that I won't go into, but that'll be useful for understanding the rest of the stack. So differentiable raycasting and mapping, in this sense, fusion modules. And with this, when we put all of these together, you get the minimum set of building blocks required to build various kinds of SLAM systems. And over here in the paper, we show like 3 different use cases. One is Kinect Fusion, which builds volumetric, like voxel grid TSTF maps. But Kinect Fusion style approaches will not scale to large environments because you would need efficient ways to encode these voxel grids. So on the other extreme, we have ICP SLAM, which is just SLAM on top of point clouds. So you keep fusing all points in your current point cloud to the map, and you keep doing this forever. But what this would do is this would cause an explosion in the number of points with time. And ideally, you would want that if scene surfaces share the same points, you want to merge them into a single point as opposed to have like, I don't know, maybe 100,000 points representing this wall. So in between is a compromise, which is a circle map. We call this point fusion. And this is based off of the point-based fusion paper from 3DV, which came in, I think, a couple of years after the Kinect Fusion paper. And this is by far the most memory efficient differentiable SLAM system that we have in our library. And the key observation here is differentiability does not impact reconstruction accuracy at all. And the only overhead it creates is in terms of memory, because you additionally want to store this computation graph in addition to just storing the SLAM estimate, which is the most recent estimate of the trajectory in the map. So we've tried this on real data as well. Like this is a sequence from the TUM RGBD benchmark. And this is a sequence which was actually collected at CMU. You can see the RI mug here. And yeah, 2 of my favorite books in the sequence as well. So the thing that I'm most excited about when we like build this differentiable SLAM system was we wanted to see what the gradients actually denote. Like it's good that you have an end-to-end differentiable SLAM system, but what does it mean for the SLAM system to be differentiable? What do gradients actually denote? And in our case, the gradients denote the contribution of each and every pixel in each RGB or depth image to the eventual reconstruction. So here's a simple illustration. There's this RGB and depth image. I'm not showing like the other RGB and depth images. This is just showing the first. And you pass it. You pass a sequence of images through Grad Slam, and you get a noisy reconstruction. And the noise is mainly because the depth we use here is noisy. And let's say you compare it with a reconstruction obtained from clean depth maps. And by comparison, we just mean we take voxel-wise L2 difference, and you backprop this error all the way through to the input image. And I'm not sure if you can see this, but you see this camera frustum-like pattern that emerges, and there's noise on the edges of the image because that's where the error is highest, because the areas inside have relatively flatter intensity values. And in the bottom sequence of images, we cut out a hole in the RGB and depth images, which leads to a reconstruction that has a gap. And we compare this reconstruction with the clean reconstruction and backprop all the way to the image again. And now if you were to take the difference of these two gradient magnitudes, you get a high response at the pixels that were cut off. So this difference in gradients is indicative of the difference between the reconstruction. So it indicates regions in pixel space or image space that cause the greatest error. And to show this in action, we have like a square that is spawned right in front of the camera, and it's in between the camera and the scene, and the occluder keeps moving. And in all cases, Grad Slam is able to like accurately propagate gradients to the image pixels containing the occluder. And what this means is if you're able to define an error over the output of the SLAM system, like over the 3D map in this case, you can backprop all the way through to the input images and figure out how do the images impact the error. And once you can do this, you can flip it to do inverse problems like what RGB or depth values do I need to make this error go down to 0? So the what we do here is we take a depth map and initialize it with noise, or in this case, not noise, but we initialize with a depth estimation from an off-the-shelf neural net. And since the neural net has not been trained on this particular sequence, or this distribution of depths, it produces a very poor estimate to begin with. But using Grad Slam, you can optimize, and after a few iterations, you can already see the chair beginning to take shape and the edges and contours of all of the other furniture in the scene and so on. And if you run these for a while, and if you have like noisy RGB and depth initializations, after a while, you get very accurate RGB and depth optimized estimates. And on the right, you see the ground truth. And because we have differentiability with respect to every pixel, we can also interpolate values for pixels that are missing depth measurements. And you can see that we fill in pixels with missing depths here. And so just before I wrap up this section, a few take-home messages are differentiating through a SLAM system is an interesting way to compute the contribution of each pixel to the 3D map. And you can kind of use these gradients to help learn representations that are consistent across views, because the SLAM system inherently imposes multi-view consistency. But there's a few drawbacks in that Grad Slam on its own requires 3D supervision, because the output of the SLAM system is a 3D map and a 3D trajectory. So you will need supervision on that output space. And long unrolled graphs also lead to exploding gradients, especially when you want to unroll over hundreds or thousands of iterations. So one way we've been trying to address that is trying to close the loop between differentiable SLAM and differentiable rendering. So you have a bunch of images. The SLAM system produces a 3D map, and the 3D map is then rendered via a differentiable rendering engine to images. And the idea is if everything in between is perfect, you should end up with the same images. So you see an optimization example here where the image on the right, it starts from noise, but using this cyclic consistency loss, you're able to recover the original intensities just by backpropagating through this entire system without using any form of 3D ground truth, like the input images are themselves used as a ground truth. And we've also extended this, and credit on this particular project goes to Sarush, who was also very instrumental in building the Grad Slam library. Sarush has been experimenting with trying to do material property estimation using Grad Slam in the loop. And if you're interested in trying out Grad Slam for some of your own projects, you might just want to try using our library, and I'd be curious to hear any thoughts that you have on this front. Before I move to the next part of the talk, if there are any like brief questions, I think I can take a couple. All right, so let me just go ahead and I'll take questions in the end. I see a raised hand.
I think I see a raised hand. Let me just.
Hello. I was just curious about the reconstructions of the gradients you had shown to visualize what actually Grad Slam is focusing on. So could you like go over what exactly those operations were performed on those gradients to get that visualization?
You mean these?
Yes.
Sure. So let me just find a slide. Yeah. So for this particular visualization, we compare the reconstruction provided by Grad Slam with a true reconstruction. And the true reconstruction is basically passed through Grad Slam the noiseless RGB and depth stream. So you get a clean reconstruction. And you compute a voxel-wise L2 difference in this case. But in some of the other examples that I showed, we do it using point fusion. So they're point clouds and you compute chamfer distance or similar like point cloud distance metrics. Or here you just use voxel-wise L2 difference. And you'd backprop this error all the way back to the image. So you compute the gradient of this error with respect to each image pixel. And you do the same for the row below, and you just subtract these two gradient maps.
All right, that makes sense. Thank you.
All right, so for the next part of the talk, I'm going to jump into something different. And then in the end, I'll talk about how this connects to Grad Slam and where, what are the missing pieces of the puzzle that need to be solved. So this is a recent work co-led with Chris Ajia, who just finished his undergrad at the University of Toronto and is soon moving to Stanford for a PhD. And this was also in collaboration with Mohammad Khodir, Onra Miksik, Vibhav Vineet, Mustafa Mukadam, Liam Paul, and Florin Chakrathi. And the key problem that we investigate in this paper is when you think about maps, the idea again is you want maps that are optimized for downstream tasks of interest. You don't necessarily need general purpose maps for all tasks. And in this case, we look at particular classes of maps called 3D scene graphs, which I'll go into. But the idea is you don't need access to the full map when planning tasks that only require you to access parts of the map. So if all you need to do is slice a few vegetables in the kitchen or like transport an apple from a kitchen to a bedroom, you don't need to reason over the map of an entire building. Rather, you need to identify what are the most likely regions that you will reason about and sparsify the entire map so that you only have a subset of these regions, and that makes planning a lot more efficient compared to trying to plan over the entire map. So the kind of maps we're using in this work is a 3D scene graph, And incidentally, I think 2 or 3 weeks ago, when Luca came and spoke about the future of SLAM and some of his research, I think a significant chunk of that talk was also focused on 3D scene graphs. And the idea of 3D scene graphs are construct hierarchical representations of a scene that encode all of the metric, symbolic, and topological properties and relational attributes. And you can see a sample 3D scene graph here, which has various levels of abstraction, and each level of abstraction is useful for a slightly different task. So here's an example where a scene is divided up into objects and places, and then rooms, and you have floors, and you eventually have buildings, but you also have attributes, either unary or binary attributes that are useful for task planning. So if you wanted to know if this object is something you can pick up, you need an attribute that says you can pick this object up, and so on. And 3D scene graphs are essentially these hierarchical representations. And there have been multiple ways of constructing these 3D scene graphs, but they haven't yet been used in very complex task planning problems. So 3D scene graphs have been used in things like semantic path planning or searching for objects in a house or small scale task and motion planning. But we wanted to see if these kind of scene graph representations were actually ready to be used in large scale tasks, which involved planning, like complex task planning. And for that, we went ahead and constructed a benchmark of task planning problems. And we used the Gibson dataset. It has 140 building level scenes with annotated scene graphs. And what we do is for each 3D scene graph, we annotate plannable attributes. So, we annotate things, affordances or modes of operation that you can use with each object. There are objects you can pick, there are objects you can open, and there are objects you can kind of toss and so on. And we basically annotate all of these attributes for each 3D scene graph, and we define 20 different planning domains. And I'll go into the domains soon. Each domain is like a class of planning problems. And we evaluate 18 classical and learning-based symbolic planners. And the kinds of tasks we use are the first task over here is rearrangement. And rearrangement is a recently introduced task or a recently introduced formalism that spans a set of tasks, which basically involves finding a bunch of K objects and then transporting those K objects to specific destinations. And we have a variant of the rearrangement problem, which is like a courier problem, in which case a robot has something like a knapsack that can store a fixed capacity of objects, and each object in the scene has a different weight, so it will take up a different number of bag slots in a knapsack. And this effectively embeds a combinatorial optimization problem into a rearrangement problem, making it very, very challenging for existing planners. And we have lifted versions of these tasks. And the difference between grounded and lifted variants is grounded variants are defined over specific instances. So it would be like, bring this apple and put it in this refrigerator. But a lifted task would be bring any apple and put it in any refrigerator. So lifted tasks are much more complex because of the inherent ambiguity in the task specification. And we evaluate all of these planners on all of these benchmarks. And I just show like 6 here because it's cumbersome to show all planners on all benchmarks. But the long and short of it is optimal planners, or planners that try and achieve optimal length plans, like plans of shortest length, for example, they do not perform in any of the large domains. So they are able to solve only the smallest of domains, the rearrangement, one object and two object, and in tiny scenes. And in all of these, if I remember correctly, the timeout was 10 minutes for most of these planners, but for the optimal planners, even if you let them run for a day, like we've actually let them run for 2 days as well, and they wouldn't solve all of these problems because there are just too many states in the scene graph to explore. So it was surprising to us that optimal planners, or even satisficing planners, where satisficing planners just attempt to find one feasible solution without worrying about the length of the solution. We were surprised that they were quite slow and incur a lot of failures in some of the more complex domains. And often they take multiple seconds to kind of come up with a solution, and they fail a lot of the time. And satisficing planners, as I said, they're slow, they fail. And the best performing class of planners are recently proposed learning-based planners that prune the state space. So these planners take the scene graph as input, and then they prune objects that are not suited for the current task. So given the task specification, given a map, they score each object according to an importance criteria, and they retain only objects that are that have importance scores above a certain threshold. And this exponentially reduces the number of planning iterations. So as you can see here, as the number of extraneous or irrelevant objects increase, the planning time shoots up from a few milliseconds to, all the way to 2 minutes. And in the scale of building scale scene graphs, you can see that nearly all objects, except for a very sparse set, are going to be irrelevant or extraneous to the task. So the questions we ask here is, can we come up with a principled way of sparsifying a scene graph given a task specification? And we do that by proposing a method called scrub, as you can see here. So the central idea is you need to tackle this problem from both ends. So you need to sparsify scene graphs so that they're very, very small and you can plan on them very quickly. And you also need to exploit scene graph hierarchies when you want to design learning-based planners. So this the first technique we propose, called scrub, essentially starts at the task specification and then works back all the way up the scene graph, so, in a way that it retains all scene graph nodes that are potentially useful for the task. And the scrub policy involves a single traversal of the scene graph, and a single traversal is linear in the number of nodes of the scene graph, so it takes only a few milliseconds. But once you've scrubbed the scene graph, the planning time, the number of operators reduces by a large fraction, especially for some grounded domains. And because of that scrubbing process, you get a huge gain in performance because you have very few operators and very few state variables. But you can see that in lifted domains, scrubbing does not help so much because in lifted domains, your goals are very ambiguously specified. If you want to talk about all apples in the scene, then you're likely to retain all apples, their ancestors, and everything that's needed to satisfy the task specification. But we see that in Scrub, it reduces the planning time by a great deal. So a lot of the classical techniques outperform learning-based state-of-the-art planners just by running the simple Scrub pre-processing step. And even where they do not outperform learning-based planners, they get like the time to plan drops by almost 50% in most of these cases. But we still see that there's a lot of replanning iterations that are incurred by state-of-the-art planners. So we propose another procedure called seek, which tries to leverage the structure of the scene graph so that it improves the efficiency of learning-based planners. And learning-based planners, they typically are supervised in the sense that they have a demonstration which marks each object as important versus unimportant, and then they train a neural net, a graph neural net, to score objects in the 3D scene graph. And what that does is it tends to remove objects that are somehow critical, like objects that are not directly related to the task, but objects that hold or connect objects of interest and so on. So in Seek, we leverage the structure of the scene graph to make sure that we have a procedure that ensures at each step, your scene graph is a valid scene subgraph. And that improves the planning efficiency and like reduce the number of replanning steps by an order of magnitude. So you can see for the rearrangement tasks, like Ploy, which was the state-of-the-art planner, it takes orders of magnitude, like close to 150 replanning iterations. But after seeking, it just takes a dozen replanning iterations. And together, what this means is there are generic representations like 3D scene graphs that people are constructing. And I personally think this is a very exciting area of research. But when you want to use these maps for tasks, we need to question how efficient are these maps going to be in downstream task planners. So you want to build maps that make downstream tasks easier, not the other way around. So there are like holistic representations, for example, 3D scene graphs in their raw form. They're not amenable to optimal task planners, but we show that when you scrub a 3D scene graph and you only get the parts of the scene that are relevant to a task, you can actually run optimal task planners over them. And it's just in a matter of minutes, you get optimal plans, as opposed to like waiting 2 to 3 days and still not getting plans. So I guess I'm about 4 minutes over time, but this is my last slide for today. And the core takeaway message that I wanted to convey is when we build maps as SLAM researchers, we need to be questioning how these maps are being employed in downstream tasks. And one way that we could do that is by leveraging differentiable programming to build SLAM systems that are inherently differentiable that can be optimized within a task, like within task planning loop. But eventually, when you want to do very high level task planning, the idea is you take in sensor data and you convert them into dense metric maps, but then you abstract them into symbolic or topological representations and you use your planners over them. So you kind of need to co-design these abstractions. And while 3D scene graphs are a promising way of co-designing these abstractions, there's still key questions in trying to address how are these, like we need to ask ourselves, how amenable are these representations to downstream planning? And this brings me to like a few missing pieces. And ideally, these are the areas that I'd be very interested in over the next few years. Like you have a mechanism of building maps differentiably, and you have a differentiable sparsification mechanism to ensure that things like 3D scene graphs are amenable to downstream tasks. But going from the dense metric representations on the left to the representations on the right in a way that preserves differentiability is still an open challenge. And also there's an open challenge as to how you would actually execute these actions in a control loop. So the control loop is still not in play. And ideally, maps that are best tuned to all of these downstream pipelines are a very promising way I see of designing these minimal and compact but efficient representations. That really was my last slide, and I'm happy to take questions at this point.
Thank you so much, Krishna, for a really nice talk. This is very exciting work. So yeah, at this point, if anybody has questions, please do post them or feel free to raise your hands. Yeah, maybe to get things started, I have a question for you, Krishna, maybe more high level, but so I like your the idea of thinking about learning these perception models end to end for task specific goals and thinking of it as part of this entire framework. I'm curious to know like what you see as the bottleneck, right, in achieving this sort of a vision. Like, is it the fact that we do not have differentiable libraries, or is it that the underlying algorithms or optimization algorithms that we use are not differentiable? So should we be coming at it from the algorithmic side or from like building better library side? Just your general thoughts there.
Yeah, Like great question. And I'd say the approach is somewhere two-pronged. And like one caveat is I don't necessarily think differentiability would be the solution to all of these problems that we currently encounter, because at some point you'll run into decisions that are inherently non-differentiable. Like you have two objects to pick, which one would you pick, A or B? And that's an inherently non-differentiable decision. But that's where I think there's this great promise in terms of integrating some of these modern neural net architectures, especially ones that reason over graphs and so on. So there's like learning that can be used very effectively in decision making or planning. But then there's also parts of the classical robotics stack which are quite useful. And what I see currently is the community trying to just prefer one solution or the other. So there's like solution stacks that are entirely based off of classical tools that we all know and have had years of development. But then there's another set of solutions that rely almost entirely on model-free learning. So I see the solution somewhere as a middle ground, but when you want to do this middle ground solution, it is very hard to think about how these two very different paradigms are going to interface with each other. So I see the interfaces as the most challenging aspect moving ahead.
Definitely. I think we have a question coming in. Yeah, okay, maybe to follow up on that. I think it is exciting in the sense that like you have like data-driven models coming together from the classical side and from the learning side, people looking at more model-based approaches. I guess I'm curious on you talked about unrolling algorithms being popular right now, like that's what you're using for Grad Slam. Like how much, where do you see like the limitations of unrolling as a method show up, like in like practical applications for SLAM, for example, like you talked about large unrolled graphs or even like the train test mismatch. Yes.
Yeah, I think that's a very timely question. And I like to take this moment to also like plug some excellent research that other groups have been doing on implicit differentiation. So I don't think unrolling is a viable solution, especially for long horizon planning or even long horizon mapping. And the best we've been able to do in terms of Grad Slam is scale it to a few thousand frames. But if you wanted to scale it to something like the size of a building, I definitely presume there'd be problems unrolling. And one very successful tool that people have been using in contexts that require unrolling is computing derivatives implicitly as opposed to maintaining explicit unrolled computation graphs. And you can, one scenario that keeps cropping up is in differentiable physics engines, where you do typically thousands of computations a second. And if you want to run a 5 to 10 second simulation, you're left with a computation graph that needs to backprop through tens of thousands of time steps. And since this becomes very intractable, you would leverage properties that are somehow invariant, such as the fact that you're minimizing an optimization objective or that you're conserving some physical quantity. And that ends up defining a property that you want to preserve, as opposed to like trying to just track the state change of a variable. And that's a more viable alternative. And I see that being used a lot these days. I also noticed that there was recently a JAX library that was announced that implicitly supports, supports as a first-class citizen implicit differentiation. And I think the community is building very exciting tools at this point.
Yeah, definitely agreed. Yeah. Sorry, go ahead. Yeah,
the other point I want to make is another way to scale these techniques is by the other way that people have looked at differentiating to otherwise non-differentiable solution schemes is to design or do probabilistic sampling. So you would have some form of reinforces, like one very simple sampler, but you can think of various other gradient estimators that are tailored to a particular non-differentiable system. And I'd argue that it's an equal amount of work trying to tailor a gradient estimator for your system while ensuring its low variance and so on, as much as it is in building or re-engineering your system to be differentiable.
All right, great. Thanks, Krishna. So I am going to switch gears and ask you another question that we have coming in, which is about the question of doing SLAM itself, which is that what could there be approaches where a SLAM system is essentially not required? So, for example, like having very direct perception and action loops and using those. What are your thoughts there?
Of course, yeah, and I guess my whole like point that I tried to make during the talk was SLAM systems need to be tailored to a task, and I would totally agree if this were taken to the extreme and there were a task that did not require math. The SLAM system should basically be just an identity mapping, passing everything that's coming in through. And I can think of a few scenarios. For example, think of a drone whose goal is only to stabilize. So it maybe needs reactive sensing, or a car that needs to drive down a road without bumping into stuff. The only goal for it is to not bump and like maintain a consistent heading. So for that, perception is actually enough. And in fact, in one of our papers, it's called MapLight, and it was led by Teddy Ort from MIT. We showed that when you have a reasonably high level plan, you can use a very sparse topometric map, something like an OpenStreetMap, to drive down multiple miles without colliding, purely relying on a combination of the topometric map, like OpenStreetMap, to provide you waypoints, but then between waypoints, you only leverage reactive, like sensing.
All right, thank you. Krishna, I have another question. I'm just parsing that. Okay, the second question is more about the scene representations that you talked about. So do you think gradients are the way to determine the utility of these specific visual or sensor-based representations for robotic tasks? Or do you see other approaches for learning such representations, such as contrastive learning?
Yeah, that's another exciting question. So I'm personally very excited by the idea of attention and how you might use that to attend to regions of an image or a map that are most interesting. For example, in the last piece of work in taskography, we kind of train a graph attention network to attend to nodes in the scene graph that are relevant given a task specification. I think some of those ideas also extend to things like differentiable SLAM, where you have a differentiable SLAM system in the loop, but then you have an attention mechanism that sparsifies an image and only focuses on objects of interest. So if your task is just to pick the red cube and like put it into a receptacle, ideally your perception system must learn to ignore everything except for red cube and the receptacle, and perhaps a few other features that are necessary for localization. So yeah, I think I'm quite excited about attention as a mechanism. And I'm also interested in trying to see how some of these implicit map representations turn out to be useful.
Yeah, okay, sounds good. Yeah, maybe then, like, I think this ties well to the second half of your talk, like this discussion where you were talking of scene graph representations and learning models there. So how do you see like these ideas come into play into that work where I guess there you were learning models for task specific applications, but like how would you go about learning representations differently, maybe incorporating attention or the things that you talked about?
Yeah. So, I mean, the notion of attention really ties well. I'd argue more to the Grad Slam style approaches. Like you have, so the way I think about this is think about the spectrum between sparse and dense SLAM. So you have sparse SLAM where everything is handcrafted. You define what feature descriptors are, like you detect features and then you describe them, and there are a few characteristics that you want each of these to hold. Like there have been various design decisions. Some preserve orientation, some don't, and so on. And at the other end of the spectrum is dense SLAM, where every pixel in every image is part of the map. So there's like handcrafted points and images that are parts of the map, and there's every pixel in every image. And attention is somewhere trading this kind of spectrum where the robot or the perception module gets to decide which pixels are to be part of the map. So I think of it like you have an attention mask that's applied to the input to a SLAM system, and the SLAM system only sees everything that's in this mask. I mean, that's my view of how attention fits into all of this. But I agree that there's a big gap between these kinds of metric representations and how we extract topological or relational abstractions out of them. So Luca's group has been doing some amazing work on trying to build these, although I think the gap is trying to build them real time and trying to build them online. But it's promising that we have solutions that build these at least offline representations. And there are still challenges though. Like you have things like scene graphs, you want to be able to use them online. And I think some amount of work needs to even go there, trying to see how you can use these scene graph representations. Like localization in scene graphs is an open challenge. At what level of abstraction do you actually localize yourself to? And the task, in the sense, defines where you need to localize. If the task only requires knowing which room you're in, it's enough if you localize at the room level. But then if the task requires precise manipulation, you'd want to localize in metric levels.
Yeah, so it kind of ties back also to the task-specific representation, what you need like in the end. Yeah, definitely. Let me see if you have time for a question. I think your last comment probably answered a question that we have on more where the question is about like how do these graph-based representation, do they help you do better planning or do a better search over the graph? So maybe like one quick comment on that, and we could wrap up after that.
Yeah, sure. So I think these graph-based representations are quite useful. As we've seen, we can sparsify these graphs and do real-time planning, which would otherwise have been infeasible. But at the same time, the open question or the more challenging aspect of this is how do we build these representations without too much handcrafting? Like currently for 3D scene graphs, there's lots of handcrafting, both in the design of the scene graph hierarchy. So what are the levels of abstraction you want? Do you want rooms, places, and how do you define a room? How do you define a place, and so on? But I think ideally you want to automate as much of these as possible. And that's where there's lots of interesting research challenges.
Sounds great. Yeah, I think it is an exciting time to be in the field, and there are a lot of interesting challenges, definitely. And with that, Krishna, we should bring this to an end. Thank you so much for taking out the time and sharing your research with us.
Yeah, thanks. It's fun being here.